any questions about yesterday's lecture? No? Okay. Maybe what I'll do anyway is to give a brief recap of the final part, which maybe was a bit fast. For two reasons, because, well, one of them was probably a bit too fast. But second, that some of the things I was saying are kind of current areas of research, and it's good also to, apart that you learn basic material, to see that sometimes with basic material you can get very close to the boundaries of what people are doing. And that's hopefully more interesting than when you do something that's very far away from the boundary. This is very close to the boundary. So yesterday what we said is that there was this, we studied conformal anomalies. One reason we studied them is that what we saw is that it gives a candidate for the quantity that decreases along RG flows, and that allows us to define a monotonically decreasing function that constrains heavily what flows are allowed and which ones are not allowed. And then, so this was in even dimensions. We have conformal anomalies. And the ones that were good C functions were the Euler anomalies. So the anomalies that multiplied the Euler density either in 2 dimensions or in 4 dimensions. And then the thing that we did is to realize that even in odd dimensions, including even in odd dimensions together, that there is a canonical object you can define, which is the partition function of a conformal field theory on a d-dimensional sphere, that you can define to be e to the f, some kind of free energy, that has the desired properties of FUV bigger than FIR for all dimensions. Okay? This is more or less, I think it's essentially proven in 3 dimensions. It's believed to be true also in 5 dimensions and so on. Even though in higher dimensions, higher than 4, it's not so easy to construct interesting RG flows because roughly speaking, the number of marginal deformations that you can have in a CFT above 4 dimensions is much smaller than in lower dimensions. Okay? So you have less RG flows, and usually these theories are strongly coupled, so there is less is known. Okay. And then what I wanted to say is that, so that's the part maybe I was a bit too fast, and maybe I can say a little bit without going through all the glory detail because that would take too much time, but I just want to mention it, just maybe in slightly more detail than I said yesterday, is that this quantity looks like some formal quantity that I defined, just some sphere partition function. And you may wonder whether this has a direct physical meaning. So there are 2 things to say about that. So one of them is that, first of all, the sphere partition function has in it things that are not interesting, that are scheme dependent, and we can exactly parameterize what those things are. And there's one thing that is interesting, which is precisely this quantity that decreases the RG flow. But what we want is to see whether we can give it a more direct physical interpretation in terms of things that we know we're more familiar with, like Hilbert spaces and things like that. Okay? So now I'll just sketch a little bit how the sphere partition function links to things that you may or may, at least with the word Hilbert space, which at least is a more familiar one than this language we're using. So here I'm just giving you some sketch of how to relate this to what I'll show. I think the person that did this essentially in the building is Rob Myers. So if you want to know more details, you should ask him. But essentially, the idea is very simple. I mean, I think some of the things, anyway. So what I want to do now is study the conformal field theory in a Lorentzian signature physical space. And I want to define finite time slice. So this I already drew yesterday. And of course, usually in quantum field theory, at a given time slice, I can define a Hilbert space. So I have a Hilbert space associated to this space-like region. And what I want to do is consider what's called the entanglement entropy. So essentially what you do is you fix your time slice, and then you essentially split your spatial slice into several regions. It can be one or more than one region. Okay? So for this particular application, what we'll do is in this RD-1 spatial slice, we will write down a region which is going to be d-2 dimensional sphere. Okay? So we're going to call this region A, and everything else region B. Okay, and now what we want to do is define the following thing. We want to consider the vacuum of the conformal field theory rho. So this defines some density metric, the vacuum state. So we have a vacuum state. And define the density matrix 0, 0. The vacuum in this special region, okay?
Region B, you mean?
Sorry?
Do you mean region B only?
What do you mean region B?
You have two regions, A and B here.
Yeah, so this is the vacuum throughout the whole region.
Ah.
Now we will come to the regions, okay? Now, the Hilbert space in this temporal slice can be split into the Hilbert space in region A and region B. That's essentially some assumption of locality. And then what we define, so this guy lives in the full Hilbert space. So what we can define is the reduced density matrix. Rho A, for example. And what you do essentially is take this density matrix, and you trace out over all degrees of freedom that are in region B. So you take a partial trace over the Hilbert space in region B of rho. Of course, you can do the same thing and define rho B by tracing now the other region, region A. Okay? And this defines a reduced density matrix, which, even though this state was pure, for example, this clearly pure state, this guy will not be a pure state. Okay? Any longer. And therefore, even though the entropy associated to rho is 0, okay, I didn't tell you what the entropy is, but I think you know. Now, out of this density matrix, you can define the von Neumann entropy. Associated to a density matrix rho, which is S of rho, which is minus the trace of log rho log rho. Okay? Of course, the entropy associated to the vacuum is 0 because it's a pure state. But now the density matrix associated to rho A will be an interesting quantity to study, as A and as B. You can define A as A and as B by using the reduced density matrix A and reduced density matrix B. And in fact, these two things, you can just focus on once because they are the same for a pure state. If you start, it doesn't have to be the vacuum. If you start with any pure state in the Hilbert space, the two entropies are the same. Okay? That's something that's not very hard to prove. And now essentially, okay, so something that you can always do is define a formal Hamiltonian. You can define a formal Hamiltonian by saying that rho A looks like e to the minus beta h. Okay? This is just a formal definition. Now, this Hamiltonian defined in this way need not be a local functional on the region A, say. But the thing that is proven, and of course I will not go through this proof here, is that for this very special geometry, that's why we can do things. This guy is, in fact, a charge. Okay, it's a charge. Symmetry. Okay. It's actually related to boosts. Okay. And okay, and with beta, here is 2 pi r. Okay. This guy is sometimes called the modular Hamiltonian. So I will not describe what this charge is. It's not particularly illuminating. It will be very illuminating what it is and very simple once I do a conformal transformation to the zeta space. So now what you can do, so again, so there's a charge symmetry, and this is associated to a particular conformal Killing vector that you have in this geometry. So now this region will evolve in time into this causal region, okay? And this is some symmetry of.
Sorry, I was confused what the charge do you mean here? What is charge symmetry?
So to every conserved to every symmetry, you associate a conserved current, and for every current, you construct a conserved charge. It's like the Hamiltonian is the charge associated to time translation, right? Mm-hmm. So for any symmetry, including conformal symmetries, you can associate a charge associated to a symmetry.
So what symmetry do you mean here?
Yeah, so I'm not writing that explicitly. So you have certain conformal symmetries that are acting on flat space, and then this is a particular combination of symmetries that generate this transformation. You will see it once I do a conformal transformation. It will be just a standard Hamiltonian. Okay. So now what I want to do is conformally map, essentially. So now what I want to do is represent this region by choosing some suitable coordinates in flat space. Okay. That makes manifest these spheres, okay, these foliations of the sphere, okay. And now what I do, probably I don't need to write down explicitly the change of coordinates. I do a change of coordinates. T, R, map to some tau theta, such that this metric can be written, is conformal to the metric of the zeta space. So if the region here was R, now I get R in the metric, d theta squared plus sine squared d theta d omega d minus 2. Okay? So, okay, so if you may or may not be familiar, this is exactly the metric on the zeta space. It discovers a particular patch of the zeta space. And now the crucial point is that now, since we know how operators transform and the conformal transformations, you can ask what happened to this density matrix in the zeta space. So this guy is the dimension of the zeta space. Okay? And the very nice thing that happens is that rho can be literally be identified with the generator of time translations in this geometry. Okay? So now what we have is that the entropy, essentially, is the entropy, the entanglement entropy is computed. So the entropy, properly speaking, is going to be like that. It's going to be computed by the partition function, the thermal partition function. So this is a thermal partition function because this is exactly what it is. This is the Hamiltonian associated with time. So the thermal partition function in the dimension of the zeta space with temperature, a temperature 2 pi r. One over the temperature, I guess, right? Yes. Okay. Now, how do we compute thermal partition functions in field theory? The way we do them is that, okay, so I don't know if you know that. If you don't know it, you will learn it at some point. Is that the way to do it is that you go to Euclidean time, imaginary time, and compactify the Euclidean time to have radius. So what you do is you go from tau to I tau Euclidean, and then you compute the partition function of the theory with tau has a periodicity given precisely by 2 pi r, by beta, okay? But what is this? Well, if I analytically continue this de Sitter metric to imaginary time, so of course, this is a conformal field theory, so I can forget about this. That's why this works for conformal field theories. I can forget about the conformal factor. And then what happens is that e to the s now has been mapped to the computation of a standard partition function in the sphere, if I put now a plus sign here, is everyone more or less happy that this is the metric of a sphere? In a foliation where you, yeah, it's a particular foliation, okay? And the periodicity of the coordinate tau is precisely such that you don't have a conical singularity when this circle vanishes, okay? So this is a smooth d-dimensional sphere. So this has mapped the computation of the entanglement entropy in this of course, this is a very special geometry, but anyway, who cares? To the partition function of a conformal field theory in d dimensions. Okay? So that's something I wanted to mention. It gives an interesting physical interpretation to an otherwise abstract object, which is the conformal field theory. Oh, sorry, the partition function of a conformal field theory on a sphere.
Could you repeat, please, what change of variables you are doing making now?
No, I didn't make a change of variables. I'm just saying, well, I'm doing a change of variables. It's called an analytic continuation. I'm saying that if you want to study the thermal partition.
No, I mean previously when you get this ether metric.
Oh, you want to write the coordinate transformation?
I mean, what is the meaning of it?
It's just a conformal transformation. Yeah. So this was part of the ingenuity. Even though I think this coordinate transformation was known before, but. Do you want me to write this down? Is that what you want to say? I'm just mapping one way to think about it is that I'm mapping this particular region into something simple that you recognize, which is the Sitter space. So one miracle about conformal transformation is that it can map not particularly nice geometries into something simple. I mean, you use that even in electromagnetism. You use conformal symmetry to map some crappy So some material with some boundary conditions to some one that is nicer. So here essentially I'm doing the same idea.
So is this in all dimensions? So you have while you don't have any while anomaly?
Yeah. So no, but so that's the point. So now if you complete that, okay. Now the entanglement entropy is a horribly ill-defined thing. It's full of divergences, and the point is when you do a systematic analysis, what you find is that in even dimensions, the unambiguous part of the entanglement entropy, in even dimensions is captured by the coefficient of certain logarithm, which is precisely the conformal anomaly. And in odd dimensions, there's a finite piece that is also unambiguous, but doesn't have to do with conformal anomalies. But the beauty of this is that this unifies this picture of a quantity that obeys this property. So in even dimensions, we already knew that it had to do with conformal anomalies. Now we find that there is a more general way of saying it, which is to look at the unambiguous part of the sphere partition function. It works in any dimension, even when you don't have conformal anomalies. Okay. So one other thing I want to say that's related to sphere partition functions, which is also kind of, I mean, as I said, I want to tell you things that are kind of closer to cutting-edge research, is the following interesting fact. So as I said, this sphere partition function, the only physical part, unambiguous part of the partition function has to do with this entanglement entropy. But it turns out that if you add symmetries to a conformal field theory, in particular, you add supersymmetry, so that what you get is super conformal field theory. That's how we call them. So another thing that has happened in the last few years is to realize that if you study the partition function of superconformal field theories on spheres, first of all, they have encode more interesting information. They have less ambiguities than the bosonic one, than the standard ones, simply because the theory is more constrained. And the thing that has happened in the last few years is that for very large classes of superconformal field theories, there is an explicit exact computation of this quantity. That in particular encodes a special class of correlators, of correlation functions, essentially by taking derivatives, as usual, with respect to sources, correlation functions of operators that you can compute exactly. That means that if the theory has a coupling constant, like say a Yang-Mills coupling constant, you can compute it as an exact function of the coupling constant. Okay? And this is one of the very few results that we have in quantum field theory that are non-perturbatively exact, or something that you know as an exact analytic function of a coupling constant. And the trick to do this computation, I'm just mentioning the word because you may see it again, it's called supersymmetric localization. The idea that the exact functional integral can be actually evaluated. So this has led to many new formula exact results in quantum field theory. Okay? So that's ends kind of this part of why spheres connect to cutting edge things. Now I want to go down to more mundane things. Okay, so in this talk, in this course so far, we have discussed how conformal symmetry is realized in space-time and how conformal symmetry is realized on operators. But now we're familiar with Hilbert spaces. We want to discuss how the Hilbert space structure of conformal field theories looks like. Okay? So I'll say a few things. Since Pedro is here, maybe I'll leave some things to Pedro. But we'll see. Okay, I'll say. I don't want to be too long today. I don't know why. Okay, so let's study the Hilbert space of conformal field theories. And one of the goals of this lecture, the main goal of this lecture, will be to see that just imposing constraints of conformal symmetry will immediately give us strong bounds on what is the lowest spectrum of dimensions of your operators in a unitary conformal field theory. Because a priori, now the dimension of an operator is an arbitrary thing. It could be any positive or negative number. But we will see that unitarity will give very strict bounds on what are the dimensions of allowed operators. It will tell you lower bounds, essentially, on what the dimension of the operators is. And I'll just show you a little bit how this works because it's kind of simple and illuminating and powerful. And in fact, this will tie up with other unitarity constraints that Pedro will discuss next week when one studies the conformal bootstrap for the 4-point function. Okay. Okay, so we have a Hilbert space. So this is something that probably don't have to give too much background is what the Hilbert space is. But the thing to say is that in a unitary quantum field theory, the symmetries of your theory are realized unitarily by unitary operators on the Hilbert space, right? So that's something that's one of the basic postulates of quantum mechanics. Of course, since quantum field theory is quantum mechanics on asteroids, it's still true. So in a conformal field theory, what we'll have to do is represent the action of the conformal group unitarily in the Hilbert space. Okay. But now, how do we define Hilbert spaces in quantum field theory? So in quantum field theory, we can define a Hilbert space essentially, as already discussed in the context of that example I told you. Essentially, what you do is you take a space-time and you foliate it by some leaves, and then there is a vector field that moves you among the leaves. Okay. And on each of these leaves, on each leaf, we define a Hilbert space associated to that leaf. Okay? And then on that leaf, you can ask, how do I evolve my states? You have a set of states that live here. What you want to, now you can ask, how do I go from one leaf to the next? Well, what you have to do is construct evolution operator. So what you need is an evolution operator that is conjugate to the generator, space-time generator that moves you geometrically up the leaf. And this acts, so you have some unitary operator in a unitary theory that will act like this if you want to move from this leaf to this leaf, okay? Good. So for example, if I have a state here, psi1, and I want to move it here, you'll get a state psi2 here, okay? So this, of course, you're familiar with in a less pompous way of saying it, by using the standard quantization that you find in textbooks. But I'll mention some other cases which are important in other areas of physics. So familiar examples, or maybe, okay, familiar maybe too strong a word, but at least the first one is totally, well, I hope it's familiar, is when you take your Minkowski space and you foliate by time slices, essentially. Okay? So you have each time slice, you have x not equals 0. You have, say, x not equals 1 in some units, x not equals minus 1. And each leaf is just a copy of RD minus 1. Okay? And then, of course, the guy that moves you up and down the leaf is the unitary operator, which is nothing but the Hamiltonian. Okay? Another example that's very useful when you study sometimes high energy processes, you want to happen to a system when you have very energetic particles colliding, is to use a foliation by light cones. So you have R1, D foliated by light cone variables. So now what you can imagine, okay, I'm going to make a mess probably, but you introduce some light cone, some surface, and you define a Hilbert space, say, on this surface. So you have x plus. Okay, it was supposed to go through the middle, but what can I do? Okay, these are colors. And now you can define on this, say, time 0 slice. So I guess at x minus equals 0, you define a set of states. And you move them up and down with now a Hamiltonian, which is it's called the light-cone Hamiltonian. So it's U is e to the I x plus b plus. I guess x minus. Yeah. So this is the trickiest part to put the right things in the right place. Okay. And again, this is useful, for example, when you study high energy QCD. Okay. So now you can ask, well, why am I going through this? Because now what I'm going to say is that there is a very useful choice of a slicing that is particularly useful in conformal field theories, where we slice our geometry in a different way. Okay? And that's called radial quantization. So now we want to study radial quantization. By the way, this is something that you can study also for massive theories, not necessarily conformal theories, except that for massive theories, since the theory depends on the scale, the Hamiltonian, I mean, so to speak, the evolution operator will depend explicitly on the scale, so it's kind of disgusting. I mean, it's like doing, when you have Hamiltonian that depends explicitly on time, it's a bit more complicated, but you can use it. But this is like, fits like a glove for conformal field theory, so that's why I want to describe it. So now what you do is you take, so I'm going to be in Euclidean space, and I'm going to foliate my space by concentric spheres. So I have one, the canonical one where I will define my states. So at radius equals 1. And then I can have other ones, bigger radius and smaller ones. Okay? Okay. And now each such picture, of course, is nothing but a d-1 sphere. Okay? So I can take, and one very explicit way to say it is that you can write the metric in flat space as dr squared, r squared d omega d-1. So at each point, I get a sphere. Okay?
And do we consider here Euclidean space?
Sorry?
Do we consider here Euclidean space?
Here I'm considering Euclidean space. There is a picture that I may or may not get to it where this quantization gets mapped to a more conventional quantization with a Hamiltonian with time, but in a different geometry, the cylinder geometry. But not, yeah, okay. Let's see if I get there. So now, okay, so now what operator will evolve surfaces, say from the canonical one to here? The dilatation operator, because dilatation scales R into lambda R. So now the operator that we're going to use to evolve the states is R equals ID, or I can write, more, if you are not happy with the R there, I can write it like this. Okay. So in this quantization, D, the dilatation operator, which is the thing that we were always discussing, kind of it was the hero of the analysis. Now, notice that in the previous lectures, P0 played absolutely no role. I didn't care about it at all. We cared about D, so that was the reason. So D plays the role of the Hamiltonian in the standard field theory treatment. Okay. And anyway, we already know with connections to critical phenomena, the quantities that we want to extract from a conformal field theory are the eigenvalues of the dilatation operator. These are the ones that determine the critical behavior of correlation functions. So this is the guy that anyway we care about. That's why this is tuned. I mean, this slicing is tuned to talk about the dilatation operator. So now what we have is this choice of slicing. What are the symmetries? So we have D that moves slices. And then we have a set of asymmetries that preserve the slice. So what are those? Rotations? Something else? Let's talk about continuous transformations. So which continuous transformations preserve a given sphere? So imagine I have the sphere here at radius 1. Which ones preserve the sphere? Okay, rotations. So spatial rotations, right? So you have. Well, and then a particular combination of translations and spatial conformal transformations. So okay, I think I'm saying something. Well, okay, the thing that is clear is that it will have the symmetry of the D-1 dimensional sphere, right? Mm-hmm. Which is the SO. Let me write it this way: SO degenerate. Okay. So that means that in order to represent states that live in a given time slice, I will have to give you the eigenvalue under the dilatation operator, which is the dimension, and the quantum numbers under rotations, which is some representation of SOT. Notice that it wasn't an accident that when we also characterized how the conformal group acted on conformal fields, this was exactly the same data. These were the charges that uniquely determine the representation. Okay, so with states, it's exactly the same. So now let me just write some formulas to understand what's going on. So just to formalize things, so now we have states that are labeled by delta and A. So this is just the dimension, the eigenvalue under D. And this A is just like a spin label. So it's a SOD label. With the property that if I act with the dilatation operator, here you get delta back. And if I act with the generator of rotations, I can always decompose these guys into irreducible representations of SOD. So I can write this as something like that. Have sigma mu no in some representation R, A, B, delta B, where these guys are irreducible representations of SOD acting in the appropriate representation. Okay? So it rotates the states in the representation. Is everything clear so far? Okay. So now in any CFT, there's a special state. There is has a conformally invariant vacuum state. Okay? So this is a state that is annihilated by all conformal generators. So in particular, it means that, let's call it 0. And obeys this property, okay? The same thing happens in a Poincare invariant theory. You have a Poincare invariant vacuum. In a conformal field theory, you have also a conformal invariant vacuum. That's kind of also the definition of what we mean by a conformal field theory, that it admits a conformal invariant vacuum. And now we want to construct representations of the conformal algebra on the Hilbert space. So how do we do that? So of course, acting with D and M on a state, just measure the charges. What else do we have in the conformal algebra? We have P's and K's. And now using the fact that D with P mu. Okay, so here I think I want my conventions minus I. So the whole point here was just to notice that one acted as a raising operator, the other one acted as a lowering operator with respect to the energy. So what happens here is if I start with the state delta A, now I can start acting on this state with PMs. And if I act, it just follows trivially from here that this guy will have dimension. While if I act with K mu, the special conformal generator, it will lower the dimension by 1. Okay? So the picture to keep in mind, the picture to keep in mind is that you lower the energy or the dimension. There's a percent sensing, which is an energy, which I may get back to later, either by acting with K's, and I raise it with acting with P's. Okay? That's what I mean. So in a unitary conformal field theory, if we impose that we want the dimension to be bounded from below, which is a physicality condition, just like we usually demand that Hamiltonians have energy bounded from below, we recover something that will look familiar from our study of operators, which is the primary condition. So if I want my state to have energy bounded from below, it means that there has to be a highest weight state or a lowest weight state. I mean, the notation is horrible because, but anyway, I think you know what I mean. There is a state which is the one with lowest energy in the family. So that means that if I act with K mu on that state, it vanishes. Okay? This is called a primary state. and then all the states that you create from the primary by acting. So now, in order to construct the representation, is this. So now I chosen my lowest dimension state. I will act now arbitrary number of times with P. Okay. So the operators that you get by acting in this way are called descendant states. And that's all you can get. Notice that since I can act an arbitrary number of times with P's, these representations of the conformal algebra are infinite dimensional. Okay? So this is a bit different than usually SU2 that you're familiar with. So any questions about this? This should be straightforward. So now what I want to do is discuss a bit what constraints unitarity, demanding that there is a unitary representation of the conformal group, is going to give on the spectrum of the theory.
So why do you demand that there should be a highest weight set? Because it's not clear that.
Sorry?
It's not clear if I choose some arbitrary foliation, then the spectrum of the generator of evolution operator would be bounded below.
Sorry? No, if I don't impose this condition, I can get arbitrary negative energy, right?
No, that's not clear because, for example, you're not considering energy here. You're considering instead the dilatation.
Yeah. Okay. So dilatation. This is what I said before. Dilatation is energy in a different space-time geometry. So it really is the same as energy in some other geometry. I will get to back this later if I have time.
I mean, okay. For example, states with negative energy, they are not allowed for some physical reasons because if there were such states, then the system would go to those states. Okay.
Yes.
Energies would be decreasing. And I mean,
I'm saying you that these words, if you're happy with these words, dimension is energy in a different geometry. So I'm saying that. Okay, so you're forcing me to say it. So, so consider the theory in RD. This can be obtained from. Okay, so I have here dxm, dxm. So this is just a metric in flat space, right? So I can write this like this. I can foliate by. I mean, this is another completely. It's a way of thinking about radial quantization in terms of a language that you're totally familiar with. The reason I didn't do it in this way is that forces you to talk about wild transformation, having to make a wild transformation to argue this. But anyway. So now what I can do is just do a trivial rewriting. I can write this as r squared times the r squared, or r squared plus d omega d minus 1. Okay? So this means that if I now define r to be e to some new coordinate, let's call it tau, okay? I have the following thing. And this is nothing but, and since the theory is conformal, the fact that you have this conformal factor is not relevant. The theory does not care about this factor. And then what you have essentially is this geometry. What is this geometry? Well, it's a sphere times some time direction. That's how you want to interpret it. Okay, so you have tau going up. You have say a tau equals 0. Okay, let me try to make some slices here. You have a tau equals 0 slice that maps because r, did I write it somewhere? Yeah, so r equals e to the tau. So that means that the place where you, say, canonically measure your states maps to the surface a unit sphere here, right? Okay, I guess let's use the same color, right? Moving past, moving to the past, so to the surface, corresponds to a smaller sphere. And moving to the future, corresponds to moving outwards here, okay? But, okay, so now, what is a dilatation? A dilatation was essentially looking at a transformation like that, right? Something that rescaled the radial coordinate. Well, what is this? This is nothing but the tau. Okay. So you see that in this language, you have the conventional picture where you have a Hilbert space at a given time slice with a special region. You construct your Hilbert space at a given time slice, and the Hamiltonian is just the generator that moves you up and down the cylinder. And if you want to, and what you want to do, say, is diagonalize, know what the spectrum of that Hamiltonian is. And this map essentially tells you that the result of evaluating the Hamiltonian in the cylinder is exactly the same as diagonalizing the dilatation operator in the plane. Okay. And then here you can already see some things that are important for the operator state correspondence. Typically, you want to construct in-states. So these are states that come from the infinite path. In particular, if you want to go all the way to minus infinity, you can have a wave function. You have a wave function coming from minus infinity that goes to the infinite future. Here at tau goes to minus infinity, this wave function is represented through this map to a point. So the whole region at tau goes to minus infinity gets mapped to a point. Okay, so what you have here is, what you're doing is representing the state that was living at minus infinity by some insertion that's living here at the origin. Okay. And in fact, the point is that if you have a state here, S, this is created by some operator that lives here at the origin. Okay. What else do I want to say? Yeah, so I mean, this is why dilatation is energy. And that's why here you wouldn't be unhappy if you put a constraint that the energy should be bounded from below. So that's why I'm doing it. Yeah. I may say more about this. Well, let's see if I have time. Because I wanted to study a bit the constraints. So notice that this is quite special of conformal field theories. If I give you any state here, by doing this conformal transformation, I'm collapsing all these geometry at the end of the cylinder to a point. Okay? So any state, states are usually defined at a fixed time slice, and you construct operators. Sorry, and you construct the Hilbert space on that spatial slice. In conformal field theories, I think it's kind of miraculous is that any state can be written down in terms of a local operator at the origin. Okay, so this is called the state operator correspondence. Okay, any more questions about this? Okay, so now we want to study the constraints of unitarity. So as usual, I'm running behind schedule, but right? So how are we going to start unitary? We want to ask the question of, if I demand that my Hilbert space has only states of non-negative norm, do I get some interesting consequences out of it? Okay. So something that should be pretty clear from the conformal algebra is that states at different levels are orthogonal. Okay. So you can only mix with states that have the same energy, the same dimension. Okay. So it's when I ask the question of constructing the constraints that unitarity imposes, I have to do it by looking at states with the same energy. States with different energy will trivially give you 0. They're orthogonal. So now let's start with the first non-trivial constraint, which come from level 1 state. So these are states that are created from the primary state by acting with 1p. Okay? And we want to study essentially the following object. I want to study the norm of these states in a given representation and demand that this is non-negative. Okay? So this is, of course, the statement of unitarity. So this is something that we like, but something I should also emphasize is that there are many interesting conformal field theories that describe real physical phenomena that are not unitary in 2 dimensions. So one should not go crazy. I mean, it's okay to think about non-unitary safeties. But now let's just, for fun, see if unitarity imposes some constraints. Okay? Okay, so now what I want to do is, essentially, in order to, so let's look at the following matrix. Just expand this into bras and quets. Okay, so this is just a rewriting of that, essentially. And essentially, what the statement of unitarity is the statement that this matrix has no negative eigenvalues. Okay? But in order to proceed, we have to define a suitable notion of conjugation, right? Because here I have the dagger of P. So again, this is something that one can say many things, but just to give you an understanding of how conjugation behaves in radial quantization is the following. So again, I defined my Hilbert space to have my unit circle. And I construct states by inserting operators inside the unit circle. And I construct out of states by, just like here, right? Out states come from plus infinity, in states come from minus infinity. So the same thing is like this. And then you can ask, how do I map in states to out states? What maps the unit sphere to the outside of the unit sphere? Well, it's precisely inversions. Okay? So that means that this physical argument tells you that you conjugate, the Hermitian conjugate in radial quantization is obtained by conjugating by inversion. Okay? So what means that you have an operator and I want to construct the dagger in radial quantization. What I have to do is conjugate by inversion so that I map in states to out states. Okay? Good. So now what we have to do is essentially, but this is something that already we have worked out a lot, right? We studied how all generators of the conformal algebra are acted on by inversion. And there are several key things. One of them was that under conjugation, P went to K. Of course, K goes to P. The other thing that happens is that D goes to minus D. This should be obvious because you're kind of changing the orientation of from where you're rescaling. By the way, this is also responsible for these I's that are floating around. D is anti-Hermitian, so that's why you have an I there. I already kind of finely tuned it so that it was there. And finally, since M nu preserved the slice, it's clear that this will be Hermitian. And actually, you can check this explicitly if you want to check it. Just take the infinitesimal vector field associated to each of these transformations and just replace x by inversion of x, and you will find this. Okay. Okay, so now essentially what I can do is, the whole point is that now I can replace this by k nu, right? So what I can do now is use in some sense, the more important, the most non-trivial relation in the conformal algebra, which is this. Okay. And so now, of course, I can write this Kp as pk plus the commutator. The first term will vanish because k acting on v vanishes. It's a primary operator, primary state. And then all that we have to worry about is d and m acting sandwiched between these states. But this is easy to work out. It's Friday. I shouldn't stay too long today. Probably. Okay, I don't know if the lecture was supposed to be 1 hour or 1 hour and a half, but I did an hour and a half anyway. So. Okay. Okay, so now.
So can I say again, why conjugated operator across is related to the operator O by inversion? I mean, for example, okay, consider, for example, momentum. Okay, it has some particular expression minus I d mu.
But this is how it's represented on the Hilbert space. By the way, you like the cylinder, right? So on the cylinder, and I'm doing the Euclidean cylinder, conjugation of an operator in the cylinder does that. And now if I use this map, you see that if I go back to the plane, it acts by inversion. And I think, do you know why this is true? In Euclidean time? Essentially, the point is that you have imagine you have a Hermitian operator at time equals 0, and now I compute O tau dagger, okay? This is going to give you e to the minus iht O 0 e to the iht, right? But this is nothing but O at minus t, which is in some sense conjugating by time reversal. And then using this map is the same as conjugating by inversion. The notion of conjugation is only defined once you tell me what the Hilbert space is. No one tells you priori what P and dagger is. I mean, it's not written, okay, it's written in textbook because they only do the standard thing, but you have to, for every...
You need a scalar product.
Sorry?
You need a scalar
You have to define your scalar product.
So if my theory is not symmetric under inversion,
Sorry?
If the theory is not symmetric under inversion,
But I'm doing it twice.
does the operator still exist? The operator I?
No, I can still ask.
Why should I be represented anywhere?
No, I think what he's asking is that imagine I have, you want to know why will an operator transform under inversion or what?
No. I'm just asking if I exist. Even
No, I exist. The theory may not be invariant under it.
I need to be represented under the space in and of itself.
Okay.
Conjugation by I.
Okay. Any more cylinders? No?
So why does it need to exist? Because to start with, the defining data was that identity exists and P mu always exists, but we never said that I must also exist.
No, I need not be a symmetry. I is not an operator, okay? I is a transformation. It's like saying parity exists even though the standard model is not invariant under parity.
Right, but there in the defining relation, I is a Hilbert space operator, right? Then you define the Hilbert space operator.
Well,
with the other, right?
Okay, so what are you trying to say?
So I'm just asking if it's.
Are you saying if the vacuum is invariant under I?
if I exists as an operator on Hilbert space.
But I think that's the same question. That's the same way I'm saying it, I think. So you're saying that if I, it's like, you can define the parity operator. Okay, let's forget about that. So yeah, I exist as an operator in the Hilbert space. And if the theory is not parity invariant, I guess what I would say is that the vacuum is not invariant under it. But
It's definition of dagger.
Sorry?
It's definition of dagger.
Yes.
Yeah, exactly. So why would you even need it to be represented on the Hilbert space in and of itself? I guess you need operators to be conjugation under I is something an operation that.
As I said, the theory may not, as an operator, not leave the vacuum invariant under I.
Right. So, but why?
So this was how it acted. Anyway, I think, is it clear? More clear now? Or no?
I mean, I understand that you're defining it in this way, and the symmetry algebra of I with others may not be represented on the Hilbert space, and if the theory is not symmetric. But it's not clear to me why the operator itself exists. How do you define I, for example?
Well, I'm defining this particular combination.
Conjugation by I.
Yeah. It's like saying, you would say, okay, K mu doesn't exist because I doesn't exist. I mean, that's not correct. The same. Okay. So now all I have to do is evaluate this guy on this matrix element. So let me do this quickly. I don't know how many details I should give you about this, but so obviously D by definition diagonalizes, just measures the eigenvalue, and I've chosen an orthonormal basis, so it's going to be delta AB. Okay, I guess delta mu no plus this. Okay. And the statement of unitarity is that this guy should be positive definite. Okay, so that means essentially that delta plus the smallest eigenvalue of this has to be non-negative. So now what we have to do is compute this. So of course, this by definition, what is this? Is what I wrote before, right? So this will be sigma mu nu in representation R acting in the right representation, right? A useful trick that you can do to solve this, which is very similar to, I think it's called the Wigner-Eckert theorem in standard quantum mechanics, is to rewrite this guy in the following way. So let me write sigma mu nu R as sigma alpha beta acting with indices AB, acting on delta alpha mu, delta beta mu, minus delta nu alpha, delta mu beta. Okay? But what is this guy? This essentially is the representation of rotations in the vector representation, right? So now what you want to do is think of alpha and beta as running over all the generators in the Lorentz group. So this looks like sigma in representation R dotted into B in the vector representation of the Lorentz group. Okay? The trick of doing this is exactly the same. No, okay, so this is what I've done. And now you can compute the eigenvalues of this matrix by the following trick that you know from quantum mechanics, by writing this gadget. I think in my comment I may need a 1/2, I don't know. Factors of 1/2 are running in loops, but no, I think it's like that. Let me define it like that. So this guy is nothing but B plus sigma R squared minus B B squared minus sigma R squared. Okay? This is the same trick that you use in quantum mechanics when you want to diagonalize spin-orbit coupling, that you write it as L squared, L plus S squared minus L squared minus S squared. But now, why this is a very useful thing to do? Because this guy is just the sum over all generators in SOD in a given representation. But by definition, this is the Casimir, the quadratic Casimir of SOD. Okay? So what you get here, essentially, is 1/2 the quadratic Casimir of what? So this guy is acting on a representation which is the tensor product of the representation R that your original state had with the vector representation. Okay.
So, I'm confused. If you, for example, the row in the middle, okay, you have sigma mu and you write it as sigma alpha beta. So then probably should there be 1/2, assuming that it...
Yeah, I think that 1/2 should be here, yes.
And also, what is B vector?
Sorry?
What is B vector here?
Is the representation of the rotation group in the vector representation. So imagine I asked you to write down the matrices that represent the Lorentz algebra when it acts on a vector. It's exactly that. Okay, so this stuff is just the.
So you call, roughly speaking, by B vector just this bracket. From the symbols.
Sorry,
Do you call B vector just this bracket?
This bracket is precisely the representation of the Lorentz group in the vector. So I can write all the Glory indices if you want. This is representing B alpha beta. Okay, so now they're upstairs. This runs over all the Lorentz generators. If something is antisymmetric in alpha and beta, and it acts on a representation space. But now the representation space is mu nu. So this, I could have written it sigma alpha beta in the vector representation if that, maybe that would be better, I don't know. Yeah, maybe, why don't I do that? It's exactly the same nature of this guy, except it acts on the vector representation. Let me call this a sigma v. So now what I have here, since this is just a summing over all generators square, by definition, this is like the quadratic Casimir of R tensor V. So you started with your representation. I tensor it with the vector representation. Of course, here you get the whole bunch of representations in the tensor product. And to get the strongest bound, we'll have to look at the smallest eigenvalue here. Minus C2 of R minus C2 of B. Okay, so the general statement is that delta, so this is the unitary constraint that comes from level 1 states, is the smallest of C2R plus C2V minus C2R times V. Okay? So in order to make this a little bit more palpable, so now in any dimension, you have to compute essentially, first understand how to represent what are the representations of the Lorentz group in D dimensions, and just know the decomposition rule of the vector with any given representation. So to make it this, to connect it to things that you know very well, let's look first in 3 dimensions. So in this case, the rotation group is SO3, right? And then how do you label representations of SO3? By the spin J. The vector has J equals 1, right? And now what can you get in R times V? Well, multiply J with 1. You can get J minus 1, J, or J plus 1. So now you have to look at the smallest Casimir here. And, okay. Okay, so I don't want to plug J. Okay, and the thing that you need to know is that C2 of J is J plus 1, right? So by doing this analysis, what you find is that delta is strictly bigger or equal than J plus 1, okay, in 3 dimensions. So this already tells you, for example, that if I look at a scalar operator, the dimension cannot go below 1, which is an interesting bound, okay? In fact, we will find a stronger bound in a second, okay? If you want to do it for 4 dimensions, here again, I think you would know how to do it with your bare hands, because S of 4 is SU2 times SU2. Again, an irreducible representation R is labeled by 2 SU2 quantum numbers. The vector that we need to tensor is the 1/2, 1/2 representation, right? So now if you do this exercise, what you find is that there are 2 cases. You get that delta is bigger or equal than J1 plus J2 plus 2 if both spins are non-zero, and delta bigger or equal than J1 plus J2 plus 1 if the product of them is 0. So either one of them or both of them are 0. Okay? So the more general statement that you can make in any dimension, let me just write down what the statement is in any dimension for the simplest representations. So what you find is, for any dimension, at level 1, again, we're looking at the constraints that are imposed when we look at the first tower of descendants. But we find that the scalar, that's in any dimension, okay, has to be bigger than 0, okay, than 0. For a spinor, it has to be equal to d minus 1 over 2. And for a vector, it has to be bigger than d minus 1. Okay. Now, how much? I don't want to say too much about that. Now it turns out, so of course we're not done. We did only level 1 constraints. I should do level 2, and level 3, and level 75. Okay. Now it is a non-trivial result that actually the necessary and sufficient constraints of unitarity stop at level 2. In fact, for a spinor and vectors, these are true. These are the real bounds. For scalars, you can study the same problem now at level 2. And there, in that case, what you find is that the bound is made stronger by getting this, okay? And probably I don't want to show you any of this because it's a bit over the top. So for scalars, again, this is the bound. And for spinors, this is the bound. And for vectors, this is the bound. Now, you can ask, what happens when I saturate the bound? So can you tell me something that you recognize when you saturate the bound? First of all, before we go there, so let's go here. So I can have delta equals 0, okay? So this is a bound that came from level 1 analysis. Can we say something about the operator that created this state? So we have. Sorry? Well, no, but okay, I want, so the first statement is that this guy is 0, right? There's a null vector. And this means that the operator that created this state, so imagine this state was created by O at 0, acting on the vacuum. What this means is that this guy is 0. Okay? What this implies is that the operator that creates such a state is the translational invariant 1 is proportional to the identity operator. Okay? So in a conformal field theory, the operator that creates states, the only operator that has dimension 0 is the identity operator. Okay? Now you can ask similar things about, okay, so this was for dimension 0. Now what happens when delta hits the unitarity bound? I mean, do you recognize what this number is, the minus 2 over 2?
It's a scalar dimension of the scale.
Well, free scalar field. Yes, so when it equals is the dimension of a free scalar field. And actually, you can prove more than that. You can prove that even though here we're not talking about Lagrangians or anything, that the operator that will create such a state, since this will be a 0, so when you saturate the bound, it means that there is a state that has 0 norm, right? And then you have to impose the relation that of that 0 as an operator equation. And since this came at level 2, the operator that has d minus 2 over 2 must obey this equation, which is nothing but the wave equation, free wave equation. Okay. Likewise, which I'm not going to do it here, but for a spinor, if delta hits the unitarity bound, so even though you don't know anything about Lagrangians, you can already know from using looking at the null vector, the vector that has 0 norm that gives you this saturation of the bound, you'll find that the corresponding operator satisfies the Dirac equation. Okay. So this is useful to know because if you have a random CFT and you just someone tells you the list of operators, you can already tell you something very strong about what the properties of some of the operators are. And finally, the last important case I want to discuss is the case of the vectors. So can someone tell me what's special about vectors whose dimension equals d minus 1? So this was the dimension of a free scalar field. This was the dimension of a free fermion. What is this? Also think for a second to answer this question, what would be the equation implied by the null vector that is associated to this unitarity constraint? Okay, so what would be the null vector associated to this? What is the state that has 0 norm but that satisfies this equation? Okay, and this is in the vector representation, right? Okay, so no one is saying anything, I'll say it. If you have an operator that transforms as a vector and has dimension delta minus 1, it satisfies this equation. So it's associated to a conserved current. Okay, a global current. Okay, the one that commutes with the conformal algebra. So I think there are more things I could say maybe about the state operator correspondence, but I think I'll leave it. It's Friday afternoon. Maybe it's better since I think I've been going pretty fast the last few days that I stop here. And maybe why don't you take another opportunity to ask me any question about what happened in the last week? If there was any question? Everything was clear? Totally unclear?
I think it was better, for example, you say everything was slowly and more detailed.
Okay, so ask me a question.
For example, I didn't understand in the last step, okay, how did you come from PMU acting on state to PMU acting on the operator?
Yeah, so this is the thing, okay, admittedly I was a bit too fast. So this was this idea of operator state correspondence, right? So I was telling you that any state here in the infinite past through this conformal transformation can be represented by doing some boundary condition near the origin in the plane, okay? And you can ask, the way to interpret this is that this state is created by inserting an operator at the origin, acting on the vacuum, okay? So for any state, there's an operator that when acting on the vacuum gives you the corresponding state, okay? So if I have an equation like P mu acting on a state, this can be turned into an operator equation, right? Acting on the corresponding operator O. So that's all I was doing here, essentially. So I had a statement that the state was annihilated, say, by P mu. And now what I have is a statement that this, sorry, okay. So maybe let me do this case. Well, this is what I did here, essentially, okay. So I have this. This is the same as a state O okay. Now, how is P mu acting on the state like that represented on O? Is represented by the commutator of P mu on O, acting on the vacuum. And now you use the thing that we constructed in the lecture, right? That you know how conformal transformations act on operators. This is nothing but the derivative operator. I mean, translations act on the operator as derivative. So that's why if this was 0, we concluded that this guy had to be translational invariant.
So these equations are only valid at 0, right?
Well, but then you can use translation generators to move them away from 0, right? Anyway, so I think next week Pedro will start. If you have questions, you can come to my office. I think you know where it is, course 27. And sometime tomorrow, I think, you will get a nice homework problem. Well, nice, I mean nasty. That you have to hand in, I don't know, in a week or two, I guess. Okay, thank you.